Hello everyone, my name is Carlos Morales. I run AI for Ambiq, and today I'd like to talk a little bit about what's driving the future of wearables. Quick introduction about Ambiq. We are a silicon provider. We build systems on a chip for very, very low power solutions. We've been around for the better part of actually more than a decade. And we have a family of products in the market today. The one that I use for AI is the Apollo4 and the most recent iteration of it, the Apollo4 Plus. Ultra low power device with a plethora of very carefully defined peripherals, design peripherals such that they're low power. And most importantly to an AI knucklehead like me, plenty of RAM, both non-volatile and SRAM, coupled with a very high-performing core, up to 200 megahertz. And this sits on a chip. When you think about it, running it like a minimum power of about 4 microamps, it's just amazing that you can do this kind of stuff in the small packages that we have today. And it's not just AI. There's all kinds of other technologies built in. There's really, really good analog to digital converters. There's a great graphics, audio subsystem that's designed for low power and so on. It's just really good platform for AI at the edge, at the endpoint. So let's talk about IoT and what's driving, which wearables is kind of part of IoT, right? What is driving this recent explosion that we're seeing in the space? A big part of it, a big limitation in the past that's being addressed by our solution, for example, is the power. So you can always do a lot when you sacrifice your battery life. So there was always this tension between practicality of a solution and how featureful it was. And so technologies like Ambiq, Spot are solving that for you, right? There's also material advances. The Wear conference is primarily about like advanced sensors and novel sensors. When you think about clothing as a sensor, for example, and those material advances plus battery technology and so on are just opening up new fields. Hand in hand with that, we're getting computational advances. So what used to take a whole desktop now fits on something that's basically smaller than a fingernail clipping. It's just insane. And it sits power at the same time. And then finally, what I would call algorithmic advances, which are AI and AI-like techniques like analytics at the endpoint. Before the last few years, that was just completely impractical and impossible to do. Now you can get away with really sophisticated algorithms running at the edge, and there's really good reasons for that. So what pops out of that is this Cambrian explosion. It's like hundreds, if not thousands, of solutions popping up that take advantage of these trends and start producing small, ubiquitous. A phrase I've heard at the Wear conference was disappearables, computation that disappears into your life, and valuable. So you bring all this together, and what you're doing is you're making your end user's life a little bit more joyful. Right? And that's why we're here. I mean, we're here to make money, right? All businesses are. But as engineers and as developers, it's important to remember that we're making things that make our end users' lives better. And when you make your end user's life better, they pay you, which is great because there's a lot of money out there. McKinsey thinks that the endpoint market is somewhere between 5 and 12 trillion. Analysts are often wrong, but even if they're off by a factor of 2, there's still trillions of dollars out there to be had. And that market includes things such as well understood, like products such as smart bands, smart watches. We know that there's huge. Hearables, like things that go in your ear or over your ears, huge. But you start doing other things like just ubiquitous preventive maintenance. It's super easy now to just kind of plop a device on your engine, on your tractor, on your whatever it is that you need to keep an eye on your transformers, and use AI to alert you when something is going wrong. It's just everywhere, right? And the possibilities here opened up by sensors, power advances, and algorithmic advances are huge. This is my personal view about what AI is for the endpoint market. AI is not the future. It never has been. AI is here to enable cool features, just make things that are already there a little bit better. For example, without AI or advanced analytics, you can use your 3D accelerometer to figure out whether you're walking or not, to a certain degree of accuracy. And if you remember the step counter wars, everybody was off by like 1,000. It's like a 10% error. No one. That's just terrible. So, especially if you care about counting steps. With AI, you can get a lot more discriminant. You can actually start teasing apart from that same sensor whether you're stepping, running, what's your gait like. You can take into account multiple gaits if you have gait variations. Are you riding a bicycle? Or are you riding a stationary bicycle? Is it an elliptical? You start getting into a lot of fine detail. And that can only happen with sophisticated algorithms such as AI. So in this case, what you're doing is you're making your life for your end user joyful, happier. The fact that I don't have to tell my watch that I'm on an elliptical, it just says, hey, I noticed you're on an elliptical. That may seem normal nowadays, but that is really sophisticated behavior. Likewise, and this is not so much for a wearable, but it is a really good application of AI. You can do things with just math, like bicubic interpolation, very simple to compute. And the reason you need this is because you're taking like HD images, which is what most people recorded. Most studios and like movie producers and streaming services have maybe 4K, mostly just HD, and they need to sell 8K TVs now. So how do you get this back catalog of lower resolution video to look well on your TV, look like reasonably sharp on your TV? The old way, bicubic interpolation, super easy. An intern could do that. The new way, using something called GANs, the AI is actually looking at, oh, this looks like a line. I will actually turn that into a line and interpolate the line between 2 pixels. So this is an actual snapshot from a snippet of a anime video, and you can see that the AI approach is doing a much better job of making it look good. And why do we do it? To sell 8K TVs? Sure. But also to make things more joyful for our end users. So next I'd like to talk about 4 basic ideas that I want you to take away from this presentation. The first is, and this one is a little controversial, right? Is that AI is the easiest way to do hard things. It is an easy button. It's easy for It's easy for maybe an AI person to say this, but I'll show you in a subsequent slide how AI is getting easier for everyone, and it really is the shortest path to solving hard problems, such as like elliptical tracking versus stationary cycle tracking. Point number 2 is that right now there are multiple tailwinds. Really accelerating small AI, like AI at the endpoint. Third bit is that AI is only part of the solution. I already talked about AI is a means to an end. But if you're going to have an AI-based product or a product that incorporates AI, it's important to know that it's not just AI. You have to do the sensing. It's just as important. You have to turn the sensor data into stuff that the AI can operate on. That's called feature extraction. And then you have to do something with that data. So having that entire pipeline in mind when you're designing your system is very important. And then the final and important one is that AI is practical today. I'm not talking about some esoteric thing. I'm going to show you real use cases of things that you could do with your products today. So getting into why AI is an easy button. What I'm showing you, this graph here shows the progress of a very common task in AI, which is image classification. It's a thing that tells you whether you have a picture of a cat, or you can search on your phone now for pictures of cars, and it'll go through your photo library and find you pictures of cars. This is an old problem. Computer scientists have been trying to solve image classification for decades. So if you look at this graph, it starts in 2010. That's the tail end of decades of research in image classification. At the tail end of that, data scientists or computer scientists were able to get it to about 25% error rate, which is still very high. Like, it's not a useful number. You can, in very specific domains, maybe that's useful, but in general domains, it's not. 2012, we see the introduction of AlexNet, which is really the first wow model that we saw. And immediately, this AI technique started beating the 30 or so years of research that came before it. And you can see it very rapidly. That yellow line there is human perception, human accuracy. So in 2015, we already had an AI model that was better at classifying images than the average person was. And you see that the graph ends at 2017, and it's not that I'm being lazy, it's that 2017 they declared this problem is solved. We're not going to do this challenge anymore. So this is something that was super hard to do, and AI made easy. And the reason AI makes things easy is you don't, like the traditional way of doing analytics or trying to extract a signal from, say, 3D accelerometer, is for an expert to look at it and do some DSP, do some math, and like, oh, that peak usually looks like what it looks like when somebody's walking, right? But there's lots of different ways of walking. There's a lot of different gaits and so on. And AI doesn't make any assumptions about that. What you do with AI is you just show it a metric ton of data, and it will find the important features in that data for you using statistical methods. It's no rocket science. It's not magic. Sometimes, like with DALL-E and all the recent Lambda, if you've been following the news, it feels a little bit magical. It feels like there's an intelligence there, but it isn't. It's a statistical engine that is doing some pattern matching for you. So that's why it's a more powerful way to program. The next step is using AI to program AI. So AutoML or neural architecture search are two ways of doing this. And what that does is it puts the control back to where it should have been. Like the gate, and there's somebody who studied gates and got a PhD in runology or whatever. That should be the person who's doing the programming, right? That's the person who should be identifying what data is important, what data is not important, and should be building a system around that, not an AI data scientist. AI data scientist will have to learn about shoes. It's better to have a shoe expert teach the AI. So that's what I mean by easy button. This is how it is. So next, I'd like to talk a little bit about the tailwinds that I'm seeing in the very small endpoint AI space. Small in terms of physical size, not small in terms of ecosystem. I think the most important trend I'm seeing is that researchers are finally realizing that small is beautiful, right? Small is sexy. For a very long time, the way you got your papers published is you published in the, I made a bigger model. I made GPT-3, I made DALL-E. They do get a lot of ink, and that's what's on the New York Times because the results are pretty impressive. So a lot of research cycles went that way. People are now realizing that to make AI practical, not just at the endpoint, but anywhere, you need much smaller models. And so you're seeing research into efficiency, research into model compression, quantization is getting very sophisticated, pruning is getting very sophisticated. These techniques make it possible to squeeze an AI into the chips that we're used to putting in at the endpoint. Another strong trend, besides research, is there's, now that it's getting practical, there's an ecosystem building around it. So you see dozens of startups producing tools on top of a mature AI tool chain, software stack, that is now enabling the subject matter experts to do AI instead of like people like me who are kind of nerdy. And then finally, there's the computational advances, like finally being able to do real compute at the endpoint without burning through your battery in an hour is critical. Otherwise, it's not practical. So and not to toot our own horn, but having something that sips power while doing real inference and speech interfaces and other kinds of analytics is critical to making this environment, this market practical. I've mentioned the word endpoint AI a few times, and I figured I should define it. What I mean by endpoint AI is AI that happens all the way at the endpoint, meaning your smart shirt or your smart watch or your like intelligent wall sockets. These are all examples of endpoint AI. And the reason it's useful is because the traditional way of capturing, say, let's talk about a speech interface, right? When you talk to an OK computer, a Siri, an Alexa, the traditional way of doing it is you do the keyword trigger locally, then you capture some sound waves, you send that to your phone, which then sends it to the cloud, which processes it and sends it back. So the round trip is terrible, right? The round trip, and we've all had this experience of having less than ideal latency while we're waiting for Siri or Alexa to start a timer. You're also burning power. So at Ambiq, we're power obsessed. And it's a lot lower power to do analytics locally than it is to transmit using RF, even if you're using something like Bluetooth, BLE, right? Low energy. So by processing locally, you get a lot, like orders of magnitude faster response time, which is joyful, right? It's joyful for your end customers, and your battery lasts longer. So it's all good. Now, sometimes you will have to go to the cloud, and a lot of times you do want to go to the cloud to federate data and collect it across multiple devices and so on. So that use case is still there. What I like to think of is instead of sending the raw data up, sending the waveform streaming off the 3D accelerometer, do some pre-analytics, do some tracking, alert, compression, and just send that over radio, and you're still saving power. All right. And points to whoever knows what Tanstaffel is. No? Tanstaffel is, there ain't no such thing as a free lunch. And the reason I put that up here is like, there's always attacks. To do those local analytics, you need more memory, you need more compute, and you need more efficient compute. So getting back to the 4 points, one of the points was AI is just a part of it. And here in this graph, AI is the box that says inference, which is what, when you feed data to AI model, that's what the process is called, inferring a result from that data. But for a practical system, you need to be able to sense, to capture your data. You need to be able to process it into something useful for the AI model. You do a little kind of the model itself, and then you do stuff with it. Like you start a timer, or you set up an alert, or you call the hospital because your user's having a I don't know, fainting spell or has fallen or something. So that entire process, which is a streaming real-time process, has to fit within a power budget. And we like to think of it in terms of 1 milliwatt for the entire process. Because that means that you can run your device, this device, on a couple of AA's for a year. And that means that if you have something sitting in the factory floor somewhere, that thing is maintenance free for a year. It's critical, right? It's what makes AI practical. So in terms of practicality, what are some of the things that you could do? And here I picked speech interfaces because wearables have an interface problem. Like very, very small screens, unless you're very dexterous, you can't, use that screen very effectively. It's hard to tap on this thing. So a lot of these devices are going to count on speech interfaces, even when there is no screen. You could do speech interfaces. We're all familiar with the first one, which is keyword spotting. It's that OK computer kind of interaction. It's an AI that's just sitting there spinning, waiting for that phrase to happen. There's actually pretty sophisticated software that happens before and after. But it's been very, very optimized. So that thing, you can see it runs that little kind of dotted line square is where most of SOCs operate. So keyword spotting, comfortable workload for that. Speech to intent is a really interesting model where instead of listening for a key phrase, it's listening for inflection and tone. It turns out when you say turn on the lights, there's a pattern to that. Like humans, we actually listen to the words. But if you have pets, if you have a dog, they're not listening to the words, they're listening to how you say it. And that's what this model does. It knows the shape of your intent. And it's, as an AI nerd, it's pretty cool how it works. It turns that speech into a picture using spectrographic analysis. And it does image recognition, the stuff that we talked about a couple of slides ago, on that spectrogram. And so it starts saying, hey, this spectrogram looks like somebody wants to turn on the lights. And humans, regardless of how you say it, lights turn on the lights, please turn on the lights, it's too dark in here, turn on, there's multiple different ways of saying your intent. The model kind of extracts that. It's pretty impressive stuff. And it's still something that you can comfortably do it uses more power than a keyword spotter, but it's something that you can do comfortably if you have enough RAM and you have enough battery space. Speech enhancement is not a speech task, it's actually an audio task. So task is feature. What speech enhancement does is think of it as noise cancellation for everything but speech. So you put in noisy speech, conference room, multiple people talking, there's a leaf blower outside and you're trying to have a nice meeting, and it calculates the mask of everything but the speech, and it cancels the noise out. That one is more computationally intense because you have to look back over multiple seconds and it's a moving window. And so once you start running speech to intent, unless you have a very efficient power efficient pipeline, you'll be able to demonstrate it, but you won't be able to run it in a practical way. So speech to intent, one of my favorite tasks. Looking a little further into the future, we start looking at features that require actual understanding of words. So this is the first kind of tier of AI where you start translating a spoken word into a textual word and then doing inference on those things. And this is useful if you're doing like language translation, or you're doing a conversation with your device, or taking dictation, so dictating a message or something to your device. It's something that can run on I would say a phone with a lot of RAM and serious, like maybe even a neural processor on it. It's because of the RAM limitations, I'm not seeing a lot of applications in the endpoint space yet. But remember the tailwinds. The researchers are making these things smaller, and companies like Ambiq are squeezing more and more compute and resources into small packages. So I think in the near future, we'll start seeing something in this space. So taking a step back from speech, I think speech is one of the killer apps. Of course, speech UIs, user interfaces, are very important for our constrained space devices. Activity recognition is another one. So activity recognition, every fitness band, smartwatch has some form of activity recognition today. There are some that are very difficult to do. Like it's okay. It's you know, are you walking or running? Easy. You can probably do that with a simple model. Are you cooking or having dinner? When you're cooking or having dinner, those movements are very similar. Like you're moving your hands in the same kind of way. You're staring at a pot or shoving food in your face. Hard to discriminate between those two. So you need something called a complex activity recognizer. And the reason those are important is because cooking is a context. There are some things that you don't want your watch to do while you're doing something like cooking. Like you don't want it to. The last thing I want is my watch to recommend that I meditate or go for a walk when I'm in the middle of an activity where I can't do it. I would love my watch to know that I'm on a plane. Like, okay, you're on a plane, you're not going to stand up, right? So context is something that these very small devices often lack. It's very hard for them given their limited sensors. This, I think, is one of the, adding context to your wearable behavior is a killer app. And then you can fuse all these things, right? Now you have some context, you have a speech interface, and now the context is you're in a dinner party. Okay, during a dinner party, there's a lot of people talking. You want your watch only listening when you say, okay, watch, do this. If you're alone, if you're working out at the gym or something and there's nobody around you, so the context is you're alone, then just tell your watch to do something. And you don't have to say the okay watch. You skip that step. It's much more natural. It's how you would talk to a normal person, and we want our devices to feel normal. So I introduced our product earlier, the Apollo4 Plus. This slide looks like if you've been in tech in Silicon Valley for a long time, you've seen slides like this where someone makes an exotic claim, 16 times less power, not 16%, 16 times. And so when I joined Ambiq, one of the first things I do is I go run some AI benchmarks, MLPerf benchmarks, which include power measurements. And the first time I ran it, I thought I had dropped to zero. It was like the power numbers were so low that I thought, okay, my math is wrong. Turns out you can't get the math wrong. The way the benchmark is set up, they don't want people getting the math wrong. So when I verified that was very exciting because a 10x improvement, I was measuring 13 to 16x, but even a 10x improvement is huge. It means you can do 10 times more stuff, or you can do stuff that you couldn't do before, like more sophisticated stuff. It is such an empowering, powerful advantage. It's just stop worrying about your battery because it's going to be there for you. And the way we do it is by reducing the voltage. That's what subthreshold means. So if there are any EEs in the room, you know that transistors are traditionally thought to be switching devices like binary on and off. And that's not true. These are kind of, I didn't flunk, but I almost flunked EE circuits. So they have operating modes in between the on and the off. And that's what Ambiq is really taking advantage of. We're able to make these transistors behave as the switches are intended to be. But we're able to do that at much lower voltage. And that has huge energy implications. It's real stuff. It's we pump out, millions of chips per month. So this is not some theoretical thing. Along with the silicon, of course, you get a lot of software. So we have versions of Apollo that have extremely low power Bluetooth, and you get a software stack with that. There's security, of course. TurboSpot is a way of controlling dynamically your power utilization. So dropping, going to 200 megahertz when you need it, dropping to 100 megahertz when you don't. Specifically, it's 192. That's like, we round up. So I think it's 96 and 192 or something like that. Turning peripherals on and off as you need them, because we're all kind of power obsessed over here. We have a part of the stack that enables speech UIs. We have a easy way to program our graphics, very sophisticated graphics processor. And then we have a library of neural network helper functions that help you get AI running on your chip quicker. That's all built on top of a common SDK. And the SDK abstracts all the, or makes easy to use all the peripherals that we have on our SoC, memory, RF, and so on. If you've been in Silicon Valley for a long time, especially if you've been in the semiconductor field, you've heard folks dabbling in subthreshold before. It's easy to get working in a lab. It's super hard to get it working in real world situations. So in the lab, you control temperature, you control power, you control everything, right? In the real world, you can't tell your user, hey, your watch is getting too warm, stay out, right? It has to work when you're running, when you're in the sun, when you're in the shade. It has to work when the battery's fully charged and when it's not. Those voltage variations have to be taken into account. And you're printing thousands of parts on a wafer. So making all of those parts run equally well in this domain is also difficult, right? So these are the problems that Ambiq has solved and productized as a way of productizing subthreshold. And the payoff is you get that 16x better performance. What's driving the future of wearables? It's practicality. Being able to do real things without impacting your battery life, or extending your battery life and doing the old stuff you were doing, right? Having a sophisticated graphical capability, so you can actually do dazzling, pretty graphics on your wearables or on your wall devices and so on. Having speech as an input. So you need good sensors, good audio, kind of converters, and you need sophisticated compute behind that. And then you tie it all together into multimodal models that are looking at different sensors. And you can start doing sophisticated things like fitness tracking, but also seemingly simple things that are actually super hard to do right. Fall detection. You don't want false positives or false negatives. Fall detection has to be one of those things that's super accurate. Lies depend on it. And it turns out that just looking at one source or another is not sufficient. So you need sophisticated compute, multiple sensors, and efficient ways of sampling those. All right, and with that, thank you, and I appreciate your time.